Welcome everyone to the 3D Radar Customer Success webinar series. I'm Dave Barry. I run sales for North America for 3D Radar. We're hoping that by sharing the practical applications of our customers in this webinar series, that will demonstrate the value of 3D radar and our multi-channel array ground penetrating radar system. We will start with Mike Heitzman, then we'll have Bill Owens, Chief Physicist and Geology Branch, or Chief Geologist and Geology Branch of Caltrans. And then we'll conclude with Q&A. So as we go along this Zoom, please enter your questions in the Q&A section of the Zoom, and Mike will facilitate the questions, and at the end have Bill and Paul from 3D Radar, the technical sales engineer, answering questions from the group. Further inquiries and questions, please email me, dbarry, B-A-R-R-Y, at 3d-radar.com. So let's kick it off with Mike Heitzman. Mike.
Thank you, Dave. Well, good morning to those attending from the U.S. and good afternoon or evening to all the others from around the world. For those who do not know me, my name is Mike Heitzman, and I'm a member of the 3D Radar team that's assisting in the implementation of the stepped frequency antenna array system. My background with GPR begins with the Sharp 2 program when I was with the National Center for Asphalt Technology in Auburn, Alabama. I was the principal investigator for a 2007 Sharp 2 study designated as R06D to examine non-destructive testing technologies that could detect asphalt pavement delamination. 3D radar was the GPR technology that best met the Sharp 2 criteria. Following the study phase, Sharp 2 included R06D into the implementation program in 2016, and I worked with 6 state agencies to perform a proof of concept evaluation on the 3D radar technology. The states involved with that implementation program included California, Minnesota, Texas, Florida, New Mexico, and Kentucky. Under Bill Owen's leadership, California was the first of the 6 agencies to actually purchase 3D radar system, and it continues to be a leader in deploying GPR system. Minnesota, Texas, and Kentucky now have a 3D radar system. Florida is working to assemble funding to purchase their system. And I do not want to leave out Maryland, who has 2 systems and is a leader in deploying this technology specifically for bridge evaluations. For those attending this webinar series on customer success stories, I want to recognize that Bill Owen has deployed this GPR technology as a tool for a number of applications. And whether you're with an agency or with a consulting firm, 3D radar system is a valuable tool for multiple types of non-destructive field evaluations and investigations. And with that background, I will turn this webinar over to Bill to share with you his experience in California with 3D radar. And as Dave mentioned, we'll have time for questions and answers at the end of Bill's presentation. Bill, we look forward to your presentation. Thank you.
Great. Thank you, Mike. So it sounds like we have a diaspora in our audience here. People are scattered all over the world. So to everybody who's attending today, good morning, good afternoon, good evening. Again, I'm Bill Owen. I'm Chief of the Geophysics and Geology Branch with the California Department of Transportation. And for a little bit of background, the Geophysics and Geology Branch acts as an internal consultant to the California Department of Transportation. We provide geophysics and NDE services throughout the state, And in order to support our infrastructure projects, our clients, if you will, are all internal to Caltrans and include our project design, our construction, our maintenance, and our inspection offices. GPR is a well-established tool for pavement investigation. We use it extensively to augment, extend, or even replace destructive core sampling. Caltrans has a number of years of experience with the technology, and we apply it to numerous projects for a variety of goals. So in this presentation, I'll give a brief history of ground penetrating radar efforts at Caltrans. I'll talk about our multi-channel efforts with ground penetrating radar, both pre and post Sharp 2, and also present some case histories, both as part of Sharp 2 and beyond, to give you an idea of some of the applications that we apply it to. We apply it again, as Mike had mentioned, to a number of different efforts. The focus on this presentation will just be on pavements, and we have a number of good examples that I think people will find informative. Now, the multi-channel GPR systems, there are a couple of other suppliers for it, but however, we're going to focus on the 3D radar system today, and it's essentially a two-component system. You have your hardware end and your software end. I'm going to keep it very simple. The hardware is a frequency domain controller, and you can couple it with either an air-launched or ground-coupled antenna array. And that controller allows you to collect high-density radar data at near highway speed. And that hardware would not be very useful without some software that allows efficient and fast processing capability of the large amounts of data that are collected. So Examiner is a software package that 3D radar markets, and we found that it's very efficient and fast and reduces the effort involved in our processing and interpreting of the multi-channel radar data to a level that we found that is comparable to what we can achieve with our single channel systems. Now, I can't adequately describe in this presentation all the details and performance specs for the 3D radar system. I will refer you to their website for more details, and better yet, contact them in person with your specific questions. Now, Caltrans has over 20 years of experience with ground penetrating radar systems, both with single channel systems and with multi-channel systems. Our first single channel system was acquired in 1998. We began application of 3D visualization using single channel systems in 2006. In 2009, we participated in what was at that time the largest ground penetrating radar investigation in the world. GPR data was acquired over all 58,000 lane miles of the state highway network. And our involvement in the geophysics and geology branch centered on development of test sections and quality control evaluation of the contractor data. That went on for about 3 years and was just a very, very large project. I had a lot of interesting results out of it and really pushed forward the idea of how effective ground penetrating radar can be for establishing pavement section data. We became involved in multi-channel applications in 2015 and acquired our first 3D radar unit in 2017 under the Sharp 2 program. We've completed the Sharp 2 research, and we officially deployed the system beginning in 2019. Now, after all of this, our initial goals when we started using ground penetrating radar way back in 1998 was to use it for geotechnical problems. However, our shift to NDE was very quick and was a natural extension of our geophysical mission, primarily because the difference between geophysics and NDE is essentially semantic. It's often characterized as to whether the material being tested is natural or man-made. Usually, if you're doing this kind of investigation on a natural material, we call it geophysics. If we're doing it on a man-made material, we call it non-destructive evaluation. But as we quickly realized, GPR is actually better suited to very shallow NDE applications. And so that put us to where we are today. Field acquisition costs provide a good comparison of performance between single channel and the 3D radar system. The majority of field investigations, majority of the costs are related to crew labor and lane closure support. equipment amortization is usually only a minor contribution to total investigation cost. And since the efficiencies gained with Examiner's processing capability makes the data processing comparable between the two systems, we can focus on the simply the labor for data acquisition and the closure costs for comparison between the two systems. Currently, we spec out our processing costs at about $5,600 a lane mile, and that's pretty comparable between both systems. So in this particular example, this was a single channel data set collected on Route 4 in Contra Costa County. That was 2 lanes and it was 54 feet long. So that's the equivalent of about 1,300 square feet. And the acquisition rate for that, and so back up a little bit and to state that this data was collected at a resolution comparable to the 3D radar system. And so using that as a guide, we had an acquisition rate of about 650 square feet an hour. The estimated cost for that, this is going to remain constant throughout all the comparisons. And this is basically the cost for a full shift for a crew, about $1,720. And the cost for a closure are about $7,200 for a full shift. And so we'll kind of bounce between those two when we do this discussion. So in this presentation, I'm going to focus on comparing field investigation costs between the 3D radar and single channel units. Remember that baseline figure of about $8,000 a day for single channel acquisition, because I'll be coming back to that a bit. Now, our early experience with using single channel GPR systems for 3D applications pointed out a need to improve the efficiency of our field operations. Although the single channel systems are well suited for small investigations, they're just not cost effective for large scale projects. And we were moving into some of those and finding that it was becoming prohibitively expensive to deploy single channel systems to collect kilometers or miles of radar data. So between 2014 and 2015, we were in contact with several GPR manufacturers who offered 3D systems, and we were able to get field demos to observe them in action. We had had the opportunity previously to observe field demos of the first generation version of the 3D radar hardware around 2010 during our network level pavement surveys. And during the equipment demos in 2014, 2015, we were impressed enough with the improvements made in the second generation system to commission a pilot bridge study to gauge real life performance. So the system was deployed to investigate the Vincent Thomas Bridge down in LA. That's about a mile long and took about an hour to collect all of the data compared to an hour for us to collect one line of single channel data. So what we found was that the hardware performance well exceeded our expectations. And when we were able to evaluate the software performance, we saw that there was some need of additional automation and processing capabilities, but we saw that the visualization features in it were very, very effective. And essentially at that point, we saw that there was a role that 3D radar could play in our work here at Caltrans. So we had began looking for ways to acquire the system and put it to work. And as luck would have it, we had an avenue appearing at about the same time. SHARP 2 was the second strategic highway research program. That was a program created by the Federal Highway Administration to assist state and local agencies with directed research applicable to their specific highway problems. The initial strategic highway research program produced more than 100 research results that were capable of being used to address local transportation challenges. The implementation assistance program under the SHARP 2 section provided grants to state and local agencies to deploy those research results. So we seized an opportunity there, and Caltrans applied for and was awarded 5 grants to perform additional non-destructive evaluation and research related to bridge decks, tunnels, pavements, and underground utilities. Again, out of all of those for today, I'm focusing just on the pavement applications. 3 of the 4 grant topics specifically required deployment of the 3D radar system. The grant funding allowed us they allowed us to acquire equipment and to deploy those systems for the research. However, no single grant provided full funding for the projects. So by leveraging the multiple grants, that allowed us to procure the 3D radar technology and other Sharp 2 related technology that was needed to complete the research. That research was completed in 2019, and we're now tasked with continuing the objectives of the program and implementing further quality improvements. So there were a number of goals under the Sharp 2 program that we were seeking to obtain. One of those was to validate the ground penetrating radar technology for diverse applications. Another was to bring high-speed GPR technology to Caltrans for our NDE support. With that, we sought to improve the testing methodology and reporting that we had and to see how much better we could make it. And part of that also consisted of training and technology transfer. And then finally, the development of appropriate roles, responsibilities, and business practices for collaboration. Now, this entire set of goals had one overarching goal, and that is primarily to help reduce maintenance and construction costs by filling in knowledge gaps in our infrastructure condition, such that we can better manage project risks and help minimize construction claims and delay payouts that result from unforeseen conditions. So our first deployment of the 3D radar system was dedicated to high-speed air-launched applications. We used a Chevy Express van as the payload delivery mechanism, and that essentially is a single mission service vehicle dedicated solely for GPR application. It's with the air launch system, you're limited to shallow investigation, no more than 2 feet, but typically on the order of about 2 to 3 feet. And we use that almost exclusively for bridge decks and asphalt pavements. With that system, we can acquire data at speeds up to the posted speed limit with no lane closures. In the second iteration of the system, we deployed the second phase, adapting that service vehicle payload for ground coupled applications. Here you can see that's the ground coupled antenna, that's the DXG model, mounted on a trailer towed behind the van. That type of system is better for deeper investigations, no more than 10 feet, but usually around between about 5 to 7 feet. We found in California are pretty effective. Your mileage may vary depending upon what your environment is. And in California, we have a lot of clay-bearing soils, so we tend to be limited more in the depth of penetration. Typically, best we can get with these kind of systems are about 10 feet. This ground-coupled system is better for concrete pavements and utilities. With that particular trailer, we can acquire data at about a 15-mile-per-hour maximum speed, so we have to have lane closures when we're using that system. We're in the process of trying to acquire trailer hardware that would allow us to do faster data acquisition. And also waiting in the wings, there is a new antenna model that 3D radar is producing that can soon be available for even deeper investigation. I think in countries that don't have a Federal Communications Commission, it's already available. In North America or in the United States, we're still waiting for FCC approval for the antenna to be marketed here in the States.
Hey, Bill, before you get off of that slide, just for the purposes of the rest of the group, confirm that in essence, this is the same van with all the same internal systems, and the only thing you really changed out was the antenna and the trailer.
Yeah, that is correct. The only thing that we do here, all the acquisition controller stays the same. All the other equipment and hardware that we use is completely compatible with that antenna. All we're doing is disconnecting the cable and moving from one antenna to the other.
Thank you.
Now, there are a number of outputs that we produce from our GPR results. Those outputs can be grouped into 2 general categories. First category are the analytical results. Those are things like concrete condition, depth to rebar, void distribution, and utility location and depth. The second involves the intermediate outputs that we need as part of our normal quality control. And those can include things like accuracy of our gridding functions, correlation of our depth that we obtain from ground penetrating radar data to known controls, such as either cores or design criteria, and also the accuracy of our georeferencing data. Although the analysis outputs are typically the ones we put in the reports, these intermediate quality control products are internal to the process, and aren't typically reported, but must still be archived for ISO 9001 compliance and forensic evaluation if we need it. This is our first example that I'll give you with real data. This was part of our Sharp 2 research, and we performed the 3D radar survey as part of plans for a bonded concrete overlay in San Bernardino County on State Route 247. The data outputs that we were seeking to obtain there included total pavement thickness, overlay thickness, and also potential identification of overlay delamination. We collected data over 4 lane miles at highway speed, without lane closure, with an acquisition rate of about 500,000 square feet an hour. That's essentially 8 lane miles an hour all collected over the course of less than a half-hour period. So we only incurred a labor cost of $1,720 for that entire survey, with no cost related to lane closure. So that gives you an idea of what the potential savings are there compared to trying to do that with a single channel system. Now, the ground penetrating radar response at the base of hot mix asphalt lifts can be used to detect potential stripping or delamination critical to design. And in this example, the high GPR reflection amplitude we can see at the base of the surface lift. Let's see if I can find my laser here. Well, anyway. Well, I can't find my pointer, but anyway, in the red area that you can see on this slide on the overlay delamination response.
Bill, we can't see your mouse. So if you want to use your mouse.
Okay, you can see the mouse right there?
Yes.
Great, thank you. I keep forgetting I actually have a mouse that works. So that particular area, high GPR reflection amplitudes at the base of the surface lift indicates that there's potential delamination of that surface lift from the lower pavement. Now, a bonded concrete overlay requires milling of the surface to a specific depth with the remaining pavement left behind to provide base support for the concrete surface replacement. Now, delamination reduces the effective base thickness. And here, for this particular project, the mill depth was specified at 3 inches. So in this case, about 1 inch of that delaminated surface lift would still remain after milling. That would create a condition where there would be insufficient thickness of that remaining lift to support the concrete overlay. So that required additional treatment during construction, primarily additional milling and thicker concrete at that delaminated section. And as part of the Sharp research, we collected cores for confirmation of the interpretation. We collected representative cores at the area where delamination was suspected, and also collected some control cores for evaluation as well. And the results of that were pretty good. We were pleased with the results. We had an 80% success rate when comparing the GPR interpretation of delamination to the visual confirmation that we could obtain from cores. So that gave us confirmation that use of GPR for assessment of delamination in hot mix asphalts was a potential application for real time and could actually be done in a production mode rather than a research mode. There is a caveat in that, however. The Sharp research results indicated that moisture content can play an important role in successful detection of delamination when using GPR. Our results confirmed that observation. We collected data twice at that same location. The first round was in April, and that's when we had the successful detection. And that was acquired shortly after a major rainstorm in the region, so we knew that we had moisture within the pavement section. The second round was collected in November, about 7 months later, at the conclusion of the dry summer season. Now, the difference in the results was significant in this example. Spring season moisture within the delaminated zone created a substantial radar contrast and rendered easy detection of that delamination. However, by the end of summer, the pavement had dried to the point that no significant reflection contrast could be detected at that delamination. So our conclusion on that was that for the evaluation of HMA delamination and stripping, there was a seasonal variation in pavement moisture content that would create scheduling constraints dependent upon our regional climate. Now, California has a Mediterranean climate consisting of wet winters and dry summers. There are microclimate regions, however, up in the far north that experience wetter conditions. And so there are places in California where we're going to be limited essentially to winter months to do this kind of work to detect pavement delamination. And there are parts of the northern state that might be more amenable to doing it year round. So we look forward to bringing that more on board and seeing what the results are on other projects as well. Our next example is another bonded concrete overlay project. This wasn't part of the SHARP 2 research, but it was conducted about the same time as the SHARP 2 program was underway. This project was located in Yolo County, which is west of Sacramento on State Route 113. We collected 10 miles or 10 lane miles. They weren't contiguous. They were located over 2 separate areas. But with those 10 lane miles, we achieved an acquisition rate of over 300,000 square feet an hour, essentially 5 lane miles an hour, again, at the cost of a single shift. Because we were working on a 2-lane highway and we had to stray over onto the incoming lane in order to capture the center of the pavement section, we had to have a temporary closure, which incurred an additional cost, but less than a typical complete closure. So we had about $5,000 in costs there, for a total project acquisition cost of about $6,600. Comparing that to a single channel equivalent production provides a striking contrast. In order to achieve that same level of resolution with a single channel system would require about 2.5 years of work, incurring about $500,000 in labor costs. And amazingly enough, that closure costs would run about $7 million to do that equivalent with just a single channel system. Now, clearly that's not feasible. So we compare it to a equivalent typical single channel approximations to that survey, essentially where we would collect single channel profiles along the wheel paths and the center of lane and shoulder for both directions. And using that kind of survey would take about 3 days, about $5,200 in labor costs and about $22,000 in closure costs. So that's a lot less than trying to do the 3D radar survey with a single channel system, but it's still 5 times greater than the 3D radar work. So that tells you that the 3D radar system is very, very efficient for collecting large amounts of data. Now on this particular project, there was a 6-inch mill specified prior to the overlay. And amazingly enough, the results on this particular survey found areas where there wasn't 6 inches of pavement. So the milling operation would have essentially ended up grinding up dirt, completely tearing up the pavement and going into the native ground. So that was a good finding. We were able to get that information to our construction folks before they'd actually gone into construction. So they were able to accommodate that and change their design on the fly to accommodate that unknown. Now our core comparisons here were pretty favorable. You can see in this particular example, we had a significant difference in the northbound lane and the southbound lane in the right wheel paths. The right wheel path had a total thickness of 12 inches, and the northbound wheel path had a thickness only of about 8 inches. So what that actually ended up meaning was that after that 6-inch mill, there wasn't going to be sufficient thickness in the northbound right wheel path in order to support the concrete overlay. And so that's what you're seeing in that red path along the line in that example. Now, I say that the core comparison was favorable. It wasn't as good as we would have liked. What we had found in comparing the cores to the GPR results was that the total thickness error was biased towards overestimation. Mean thickness error was about 1.1 inches. Although that increased our confidence in the no pavement interpretation, that reduced our confidence everywhere else. And there were a number of factors that might possibly contribute to that. One is, of course, operator error. We were early in the process of using the 3D radar system, and we can't discount the fact that we may have missed something in the details. Another one that was very notable was that there was poor location info for these cores. The cores were not geo-referenced. They were collected based on post mile and wheel path location. So along the direction of travel, they were only good to the nearest 0.01 miles. So that's about plus or minus 50 feet. And transverse location was only good to maybe about plus or minus a couple of feet. So we really didn't have a good handle on where those cores were. Now, in areas where there wasn't a lot of variability, that mislocation error may not have factored very much into the into our error estimates, but in areas where we had high variability, that could have made a big difference in the core correlations. Now, the earlier examiner version that we were using was a little less user-friendly. And after struggling with it for a while, we ultimately ended up exporting that data, the thickness data, to a separate application for gridding and contouring. So there may have been some intra-residual error that contributed to that as well. So we can, however, compare this earlier data with newer data. This was a project that was completed just this year, 2 months ago, actually. And using the most recent version of Examiner with the onboard tracing and plotting and gridding routines that are available on it, we found that the user friendliness was greatly improved, and the plotting and tracing technology in that new version was very, very user friendly and much easier to work with. For this project, the cores were actually collected using geo-referenced ground penetrating radar data rather than the course local project coordinates, post-mile coordinates. So the GPR data actually guided the core collection. And we can see in this particular example is that we had an improvement by about a factor of 10 in the thickness error estimates that we were deriving for these pavements. So it's very, very promising results for comparing core thickness to thickness values derived using ground penetrating radar. I'll close out these examples with a concrete pavement project. This was on State Route 8 in San Diego County. Ground penetrating radar here was acquired to assist in the investigation of pavement subsidence. We used multiple geophysical methods in this one. We're only going to focus on the ground penetrating radar here. And in this particular example, we found a couple of areas of anomalies that we identified. One was an obvious slab repair that we were able to pick up. And another was an area where there was visible pavement distress, and we identified regions of potential voids. That potential void area was identified and transmitted to our engineer, and that was cored for follow-up. This particular project utilized a ground coupled array, and full lane closure was required, so acquisition costs were likewise increased. Production rate was about 123,000 square feet an hour, with an equivalent acquisition rate of about 2.9 lane miles an hour. Now, to do a realistic comparison for this project with a single channel survey, we basically would not be doing the entire survey to do this with a single channel system. Using a single channel system, we would have only limited our survey to the area of visible pavement distress. So in order to do this comparison, we're changing from a large scale investigation with a multi-channel system to a smaller scale investigation with a single channel system. With a greatly reduced area of investigation limited to a grid around the known area of pavement distress. That's about 3,400 square feet in the eastbound lane only. And using that assumption, that would require about 5 hours for data collection and 1 day of lane closure. So for this case, the costs essentially for a single channel system or a 3D radar system would be about the same. But in this case, the improvement gained is in the increased production rate and the much greater area covered by the 3D radar system for the same acquisition cost. Now, as I mentioned, the void detection that we identified from ground penetrating radar, or I'm going to call them potential voids for ground penetrating radar, were followed up by coring. And those results were excellent. We were very, very pleased with what came out of this. Those cores showed excellent agreement with the ground penetrating radar data. Pretty much anywhere we identified a void and where they drilled, a void was found, and it was significant. These voids ranged in thickness between 3 and 5 inches. So again, very, very favorable results using it for this particular project. And that was vital information that they needed to estimate grout quantities for pressure injection and stabilization of that slab subsidence in that distressed area. So with that, I'll start wrapping it up. In conclusion, the 3D radar system has proven to be a very effective tool for the application of large-scale GPR surveys for Caltrans. It has allowed us to undertake ground penetrating radar investigations that would simply not be feasible using single channel systems or systems that have slower data acquisition rates. The hardware would not be nearly as effective without the corresponding software application needed to efficiently process and present those results. And the outputs produced provided valuable data for project design. We find that the improved quality and quantity of information can help us reduce construction claims and reduce delay payouts related to unknown project risks. I hope those examples provided here give you some idea of the scope and quality improvement we've been able to achieve using the 3D radar system. And with that, I'll be happy to answer some questions.
Thank you, Bill. I want to start with a question or maybe a follow-up on your summary here. With you working with the various groups and sections within the DOT, have any of them provided you with a level of value with respect to reduced construction claims?
I would say, yes, we do have that data available for at least one side of the house, and that is with the subsurface utility investigation. There have been a number of value-added surveys that had been done within Caltrans on the impact of unknown utilities or utility conflicts to project construction. And what they have found is that for 85 to 90% of our Caltrans projects, we've had some form of utility conflict related to unknown utilities. And the payouts for those particular conflicts have ranged from the tens of thousands of dollars to the low millions of dollars. So that gives you an idea of the cost savings that we're achieving applying this particular method in addition to other methods for underground utility locating. We've actually gotten a significant amount of our work is working within our existing maintenance stations to locate the utilities. As it turns out, most of those utilities at our maintenance stations aren't mapped. And so anytime they're going out and doing a reconstruction, or they're rehabilitating a building, or they're adding new buildings to our maintenance stations, they need us to come out and do the utility locating for them in advance of the construction. And that's where we know we've got good documented return on investment for this particular application.
Great, thank you. I've got a couple of questions here to provide to you. First one, from slide 13, you were giving a 80% success rate for identifying delamination. Did you have any success rate or failure rate where you thought there was a competent pavement, but there was actually damage?
In this particular survey, no, it was actually the opposite. We had one result where we thought we had delamination, and it turned out there was not. In that particular core, if I recall correctly, there was a vertical crack below the surface overlay, but there was not actual delamination of the pavement itself.
Very good. Have you in California, have you used the GPR, the 3D radar system, to detect dowel bar alignment for concrete pavements?
Concrete pavements are still a work in progress. The latest project that we did was for a continuously reinforced section, so there weren't there wasn't an issue of dowel placement in that one. But we have done the single channel system, and that particular example, I think I can, let's see if I can show you all of them. In that particular single channel example, that actually does have an example of where we have a misplaced dowel. So we have used it, we have used radar for that. We just haven't done it with a 3D radar system yet.
Great, thank you. Couple of other questions. Here's one I don't know that you got into, but do you have any information about using drones and GPR?
We don't do drone applications with GPR at this time. That doesn't mean that sometime in the future we might be doing it, but at this point we are not.
And just to jump in, that may have been prompted by a LinkedIn post about a new product that we're unveiling today with a drone-mounted air-coupled system. So we can give you some more information about that if you go to our website and or give us a call.
Okay, another question is what frequency antennas were used for the pavement evaluations? And I would guess that this is for the single antenna comparisons that you were making.
Oh, okay. Now the 3D radar system is swept frequency, so we're not bound by a single frequency to when we're using 3D radar. With the single channel systems, we were using either 500 megahertz or 1 gigahertz antennas for those applications.
And just
Great.
so everyone understands, just to interrupt quickly, all of our antenna arrays are number one arrays, so they're multi-channel by definition, and everything is step frequency, which means every time that we take a subsurface sample, we start at 150 megahertz and sweep through all of the frequencies to 3 gigahertz, which allows us the entire frequency response from the subsurface. So it's a major difference between our type of technology, which is step frequency, versus single frequency impulse technology that a lot of you are probably used to.
Yep.
Okay, another
And
question.
that's why I said we need to. That's why I said you needed to talk to the people at 3D Radar for better information.
Very good. With your bound concrete overlays through your forensic investigations, were you able to come up with a conclusion as to the cause, whether it was moisture damage or mix segregation? And I'm going to read between the lines, and that is whether or not you could determine that from the signal itself, the response from the GPR, or did you have to go back in core to verify that?
The actual reason, the GPR is best for doing a go, no-go evaluation for delamination. It doesn't always give you a good idea of why it happened. We've seen some examples of ground penetrating radar on HMA pavements where you can see the thermal segregation in the end dumps. But in terms of identifying the cause of stripping or delamination, really don't have a good handle on it with radar, at least not at this time.
Very good. Another question. In your slides, you mentioned that you calculated rebar depth. I think this is one of your earlier slides, and the overlay delamination. Was that done within Examiner or in separate software?
In this particular, in the examples we presented here, none of these examples actually had any rebar in them. So would this be like the general one where we talked about types of outputs?
Yes, I think it was like slide 2 or 3 in your presentation. That was all done with a single channel, I believe.
That is correct. We have other projects where we have identified depth to rebar with the 3D radar system, but the vast majority of the work with evaluating depth to rebar has been with the single channel system. We're still moving into the process of doing that for bridge deck evaluations.
Very good, thank you. I'm going to have this question here. We might have to rely on Paul to respond. When calculating pavement thickness, the 3D radar data shows you the arrival time for the reflection, from the bottom of each layer, but how do you calculate the velocity of each layer?
Okay, we can combine on this. Good question. We would recommend that you calibrate the system with core samples. So known thicknesses can be introduced to the interfaces that you've traced, and that will pull all of your speeds for the materials and your measurements to more closely match the real thing.
Great, thank you, Paul. Next question, does Examiner perform automatic rebar? Whoops, hold on, my things have jumped here. Does Examiner perform automatic rebar hyperbola picking? If so, how effective is it? And Paul, you may be a better source for that.
Sure. We have an automated interface picking tool in Examiner. And since reinforcement is in fact an interface as well, especially if you you stretch that layer out, it becomes almost a straight line as well. But you can use the interface tracing tools within our software to pick out a majority of the rebar layer. We are, of course, developing more and more tools, and you will see some vast improvements later this year. But I can't tell you too much more about that, but stay tuned for that development.
Okay, I'm going to go to this. I'm going to go to this question. Why is step frequency GPR better than impulse GPR?
It's not necessarily better. It depends on what your task is. But you can receive great resolution versus depth penetration, and if you're traveling for a long distance, you will have different materials, different ages, and qualities that will be changing all the time. And so having a wide bandwidth, sampling at different frequency, you can ensure that you get optimum results regardless of the environment that you're scanning. So it has certain advantages than picking a central frequency and then maybe not getting the result you expected from your data when you get back into the office. Right?
Great. I'm going to see if I can focus on a few questions that are specific for Bill. This one, Bill, you mounted the air coupled antenna to the front of the van and the ground coupled system to the rear. Is there any reason? Hold on. My thing keeps jumping on me. Okay. Is there?
It's unanswered.
Is it answered now? Okay, it got moved.
Okay, so the question is there any
Is there a
benefit?
reason, other than the ability to use both systems? Is there any reason for that other than the ability to use both systems simultaneously? I think I know the answer to that, but go ahead.
Yeah. Now the only benefit, you could use both systems simultaneously if you had two controllers, but we only have one controller unit, so we switch between the two. And it's basically just a practical matter in that, for an air launch system, you can mount it either in the forward or the rear, depending upon your own personal preference. For the ground coupled systems, you're typically better off putting it in the rear and trailering it. So that's primarily the reason why we put it in the rear.
Yeah, and I know from some of the work done in Maryland, the other issue with the ground coupled antenna is deviations in the profile as you're driving along. So it's done at a much slower rate, and it has to have the ability to essentially bump up and down if it does happen to come up against some type of interference with the pavement profile itself.
Yes, it's really just more practical to tow it than it is to mount it to the front.
Okay. There's a number of additional questions, but we're pushing 50 minutes already. And let me find one here. Here's one. In small scale application, utility mapping and image generation, i.e. the size of a single commercial lot, what is the depth, resolution, and accuracy of the images generated? And Bill, why don't you respond? But then I'd like to have Paul respond as well. He's done a lot of utility mapping.
Sure. And the answer to that is going to be, it depends. It depends on a lot of things. Number one, it's going to depend upon your survey parameters, both horizontally and within your vertical depth of investigation. It's going to depend on, if you're using a single channel system, it's going to be what center frequency you've selected. For horizontally, it's going to be what your station spacing is. And unfortunately, there's no easy answer for that one. It's just highly dependent upon what you've selected for your survey parameters.
Thank you. Paul, do you want to add anything?
Agreed. Bill, that's pretty much what I was going to say. That's exactly what I was going to come with, actually. Same answer, yes.
Okay, here's one specific. Will Caltrans eventually develop some design/evaluation guidelines or methodologies for GPR data gathering and analysis, similar to how you do methodologies for FWD testing?
I think in terms of contract performance, we're probably not going to be doing that. We do have our own internal guidance that we use. And that's part of our quality manual. And so that's internal to us. At this point, we haven't published it. But for contract type work, it's not, I don't see it being feasible for overall. There might be some specific types of surveys that we contract out for where there will be specifications given, but I don't think we'll be developing any kind of general specifications for it. There are a number of guidelines out there that are already available for improving and ensuring effective ground penetrating radar investigations.
Very good, thank you. There are a lot of other questions here, but I do not want to just continue on all morning, even though a lot of us would enjoy doing that. I would encourage all of the attendees, if you have a question, to pose that to the 3D radar sales group, and either Kent or Dave or Paul will respond to those. And of course, if you do have some questions specifically to how Bill is performing in California, I think Bill wouldn't mind answering a few questions there as well. But having said that, I'm going to turn this back over to Dave and let him have a few final closing comments.
Thanks, Mike. And yes, as you can see, my email is here. And so, yeah, what we'll do is we'll gather up the questions that have come in that we weren't able to answer, and maybe do a response back to the group with our answers. But I wanted to just take a second to thank Bill for the fantastic sharing of applications and the use and for the different bridges and pavement and so on. So thank you, Bill. And I think we're going to sign off here, but thank you all for attending, and we'll send you a notice when I think in about a month, we'll be having our next webinar. So thanks again, and we'll talk to you soon.